In the next few math lessons, we'll be looking at energy, specifically energy transformations. Now, the word transformations is very important because it's only through transformations that energy can actually be measured. A cube of iron contains energy, but there's no way to determine how much energy it contains. We can only measure energy while it's being transferred between objects, released or absorbed in chemical reactions or other situations in which change happens. Two fundamental ways that energy can be transferred are work and heat. We can measure both of these transformations. Now, before we go any further, I want to clarify that heat and temperature are not the same thing. Heat is a measure of energy transfer, while temperature measures something different. We'll learn how to measure heat in the next video. This video will focus on measuring energy transferred through work. First, we have to make sure we understand the physics definition of work. Work equals force times distance. That's it. But it takes some explaining and practice to really understand what that means. The formula states that if you multiply force times distance, you get work. But how do you do that? We know what distance is, but what is force, and how is it measured? And what distance are we talking about? Well, to simplify things, we can define a force as a push or a pull. So if you push a stationary object hard enough to make it move, then we can measure the work by determining the amount of force and multiplying it times the distance the object moves while being pushed. That will give us work, force times distance. But how do we measure that force? One excellent way to measure force is with a spring. The neat thing about most springs is that the greater the pull, or force, the greater the stretch. In fact, the stretch is directly proportional to the force. From past math lessons, you'll remember that directly proportional means that when the force doubles, the stretch doubles. So if the weight of this gold object stretches the spring by x, then two of them will stretch the spring by 2x. If there were 3 gold weights, the spring would stretch by 3x. Therefore, if we can decide on a standard force with which to pull a spring, then we can use the resulting spring stretch as a standard to measure force, much like a meter stick is used as a standard to measure distance. Let's take a look at how that would work. Scientists have chosen a standard unit of force. It's named the Newton, after Isaac Newton, who spent years mathematically analyzing forces and their effects on objects. 1 Newton is technically defined as the net force needed to accelerate a 1 kilogram mass 1 meter per second every second that the force is applied. But we'll get into that definition later. For now, it's simply good enough to know that 1 Newton is the force approximately equal to the gravitational pull, or weight, of the Earth near its surface on a 100-gram mass. So if we hang a 100-gram mass from a spring, that's 1 Newton of force pulling on it. If that 1 Newton of force stretches this particular spring 1.5 centimeters, then we know that each additional Newton will stretch the spring another 1.5 centimeters. Now we can use the spring to measure any force we want, as long as the spring is not overstretched. For example, if we hang an unknown mass on the spring and it stretches 3 centimeters, we know that the force is 2 newtons, because the stretch was twice what it was with 1 Newton. What's neat is that we can use the spring to measure more than just weight forces. If you were to pull the spring with your hand to make it stretch 3 centimeters, then you could know that you were pulling with 2 newtons of force. Okay, so now we have a standard for measuring force. Let's get back to work, which is force times distance. If we use this spring that we've calibrated to pull an object horizontally, and the spring is stretched 3 centimeters the whole time, then we know we're applying a constant force of 2 newtons. And if we move the object a total of 3 meters, then the work is 2 newtons times 3 meters, giving us 6 newton meters. Another name for a newton meter is the joule. The term joule is in honor of James Joule, who discovered a way of converting a known amount of work energy into a predictable amount of heat. We'll talk much more about that in later videos. It's important to note that work is done only if an object is moved by a force. Pushing a wall, for example, will not cause the wall to begin moving, so there is no work done. Your muscles may expend energy, but it is in the form of heat, not work. Both are forms of energy transfer, but they are measured differently. Work requires distance, so if a 10 Newton force is exerted on a wall that does not move when the force is applied, then the work is 10 newtons times 0 meters equals 0 joules. We have one more thing to talk about with regards to work, the energy that's transferred. Energy transferred through work can result in 3 types of energy. First is kinetic energy, or energy of motion. On a frictionless surface, pushing an object will cause it to accelerate. When the force stops pushing, the object will continue moving because there is no force like friction to slow it down. Work energy in this case has been converted to kinetic energy as the object keeps moving. The second type of energy that work can transfer is thermal energy, or heat. Unlike the last example, if there is friction between the object and the surface it's on, some or all of the work energy is converted into thermal energy. Friction causes the temperature of the object and the floor to increase. If the object stops moving when the pushing force stops, then all of the energy has been converted to thermal energy. The third basic type of energy that can come from work is potential energy, or stored energy. When an object is lifted in Earth's gravitational field, work is being done. That work is equal to the weight of the object, which is the gravitational pull on it, times the distance it's lifted. That work energy is transferred to the object as stored energy, because it can be used to make the object fall back down. So, if an object weighing, say, 25 newtons, is lifted 2 meters off the Earth's surface, the work done on the object is 50 joules. After being lifted, the object contains 50 joules more energy than before it was lifted. If the object is dropped, the gravitational potential energy will be converted to kinetic energy as the object speeds up during the fall. When it hits the ground, the kinetic energy will be converted into thermal energy and sound is actually kinetic energy of air molecules. Another way of converting work into potential energy is to pull a spring. The work is the force used to pull the spring times the distance that the spring is stretched. The stretched spring stores the work energy as spring potential energy. The most interesting discovery by James Prescott Joule is that energy is always conserved. That means it can be converted from one form into another, but it is never destroyed. We call that the law of conservation of energy. In this lesson, we have focused on work energy. In the video, Franklin names negative and positive charges. We see that when two charged rods are brought near each other, a force of one rod on the other causes it to move. Thus, electrical charges can do work when they interact with each other. That's why it's so important to be able to understand how to measure work. In the next lesson, we'll investigate energy transfers by heat.